तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the MESFET characteristics, taking into account the velocity saturation, and we have analyzed it, and finally, we were comparing some of the experimental results that people have reported. One result that we saw was the reduction in the or the change in the gate length, okay. And there we saw the pinch off voltage changing unless you change the thickness. Then we took a look into the channel length effects. Okay. What we did was we took this is actually the result reported in literature. You can see this device 1, the N plus layer is not present here on the top. Okay. In the device 2, a layer is present on the top. So, all the difference is this length, this is in this case this is the channel length, gate length is 0.25 micron, okay, and channel length is 2.1 micron. All other things remaining same, you can just watch next one and the previous one. Here that layer is absent, now that layer is present. So, in device 2, the N plus layer is right up to this point. So, channel length is actually 0.5 micron, it is as good as extending the metal right up to this point, because it is heavily doped, it is a metallic conduction. So, the difference is only in the channel length, gate length in both the cases is 0.25 microns. Okay. Now, when they measured the results on these devices, that the devices showed like this. Device 1, which does not have the N plus layer on the top, I am just summarizing what we said in the previous lecture. Gate length both same, device 2 has N plus layer. So, channel length in the gate 1 is 2.1 micron the whole thing, in the gate where the N plus layer is present, channel length is 0.5 micron. Now, GM delta ID by delta IDS by delta VGS is higher in the second case, where N plus layer is going all the way up to this point. This is the second device. If that is absent, that is 125. But now the question is asked whether it is due to the, for example, if you have it, if you remove that portion, you will have extra resistance coming from this layer. Now, this resistance is not present, whether that is playing a role in deciding this, making this difference. So, to do that, okay, just let us see how it will affect. I did not discuss it in the previous lecture. The effect of that resistance, whatever is present at the source, okay, source region between the source contact and the gate, there is a resistance, and the two resistances are different in the two cases, because when the N plus layer is present, definitely that RS is smaller. When the N plus layer is absent, RS is larger. Whether that has made the difference, that is how it would make difference. So, the definition of transconductance, ID, this is the equivalent circuit, gate, nothing there at low frequency, it is a capacitance, it is open. Okay. When apply voltage, that gives us a current ID equal to GM0. GM0 is the intrinsic transconductance, which actually is the transconductance that you get if R is equal to 0. Okay. So, if R is equal to 0, ID will be GM0 times the voltage between the gate and the source, that is VGS0. Now, that is what I put here. But when the resistance is present, okay, the VGS0 is not equal to the applied voltage VGS, because VGS between these two is shared between the VGS0 and RS. Okay, the voltage gets divided between the gate and the intrinsic source region and the resistance, because this ID flows through that, from the drain to the source through the resistance. So, that is why VGS0 is VGS total voltage minus ID times RS. So, minus this drop. So, that is what is put here. Now, actually what you do is make rearrangements, and ID will be actually equal to ID into 1 plus GM 0 into RS equal to this quantity GM times VGS. Transconductance actually in the real device is ID divided by the applied voltage. This is a small signal voltage, not DC, incremental quantities. ID divided by VGS. So, VGS is actually given by the sum of these two. So, you get this quantity. So, what you are telling is GM effective is GM 0 intrinsic GM divided by 1 plus GM 0 to RS. So, that is effective GM equals ID, okay, drain current divided by ID divided by 1 plus ID divided by VGS, which actually is equal to GM 0 divided by, I am rewriting that, 1 plus GM 0 times RS. Okay. What you measure is this quantity. What you want to take a look at is what is really the intrinsic GM 0 is. So, GM 0 from this equation you can rearrange GM 0 will be equal to GM effective divided by, just rearranging this, you can write 1 plus GM effective 1 minus into RS. I am writing it in this form because GM effective is the one that you measure, delta ID by delta VGS. So, rearranging you get this equation. So, once you know GM effective and once you know RS, RS is another quantity you can measure, all measure put together you can get the intrinsic GM. Now, just going back, so this is the approach, going back to the diagram. Okay. The RS can be measured by applying a voltage between the drain and the source and by measuring the voltage drop between this and this point. Okay. In fact, it is better seen in the previous diagram. See here, apply voltage between the drain and the source, small voltage. You do not want velocity saturation, you want the Ohm's law to hold good. So, apply small voltage, small current will flow through that. Measure how much is the voltage drop between the source and the gate. The whole thing is IR drop here to the current flowing. Okay. So, you measure the voltage drop, okay, and you measure the total current, drain current. So, total voltage drop between these two divided by current gives you the resistance between these two. So, that is the way they measured it, and then measured the GM effective also, used that equation, GM 0 is GM effective divided by 1 minus GM effective into RS, okay, from this equivalent circuit, and you get the numbers. So, I was in my last lecture I just quickly went through this, so I just thought I will go through it again. So, now you can see without N plus intrinsic GM note, corrected GM 0 is 145 milliampere per volt per millimeter width, and with the N plus it is still 245. What you are telling is the GM extrinsic GM or effective GM was higher, also the intrinsic GM is higher when the N plus layer is present. So, it is not due to series resistance, it is due to the property of the device at that particular point. Okay. So, now what are these quantities? These quantities are given by these equations. IDS is given by that, GM is given by this. So, if I take the GM in the two cases, the intrinsic GM, CS is the same. because gate is the same thing, W is the same, VGS is the same, 0 or whatever you apply. The threshold voltage there cannot be any change, because dBi minus Vp0 is the threshold voltage. Vp0 will get affected only if gate length if you change, but gate length is same, 0.25 micron. So, that will be same. So, everything is same. So, only thing possibility is that this may be different in the two devices. Whether it is true, we will see afterwards. So, that is Gm2 by Gm1 is Vs2 by Vs1. So, that you can actually compute Vs by putting all these values. So, you get, when you substitute all these values, you get 1.9 in 10 to the power 7 for second device, first device you get 1.1 in 10 to the power 7. So, ratio is 1.7. What we are telling is Gm2 in the second case is higher than Gm1, possibly because the velocity, effective saturation velocity is more when you brought the n+ layer close to the gate. Now, what we want to do is, so this is what we have summed up. Since Vp0, V threshold voltage cannot change, because Lg is the same in both cases, only change that you can see is the velocities. So, that we have just now seen, it is 1.7. Now, next job is, can this velocity be different, and what could be the reason? Just we will take a look at, go back a little bit into physics and see what models people have proposed for that. Now, before we go into those models, few things we have to see. Just looking back, what are the things that we have seen in the MESFET? If you operate in the linear region, or if you operate in a long channel device, there is no velocity saturation. It is only the square law with the multiply factor of mu n CSW by 2L. Okay? So, mu n is the one which governs the drain current and the transconductance. So, in those situations, mu n is at least 5 times larger than in gallium arsenide than silicon. What we are trying to compare is, now, is there any point in switching over to gallium arsenide? Do you get really the benefit? And if you want to get the benefit, what should you do? When the channel length is long, no doubt you will get the benefit, because this is the situation. When the channel length is long, whole thing is proportional to, okay, let me just write that down here, because I do not have it right now, there is long channel. Device Gm mu n Cs W divided by L with threshold, because IDS is mu n okay. So, now you can see, if the channel length is long, if you have a device or if you have material whose mobility is higher 5 times than that of silicon, you will definitely get the Gm 5 times. Added to that, Cs is actually depends upon epsilon s into epsilon 0 by A. If the thickness of the channel is same as that of oxide in MOS, this will be larger than that by a factor of about 3, because epsilon s, relative permittivity in gallium arsenide is 12.9 and relative permittivity in oxide is 4, so about factor of 3. So, this is factor of 3 higher compared to C oxide in silicon, this is factor of 5 compared to mobility in silicon. So, about 10 to 15 times definitely you get improvement in the transconductance. We are not worried about current so much, we are worried about transconductance, because that gives how much change in current for a change in voltage, that gives a driving capability for the device. Okay. So, Gm is the most important thing, whether you talk of bipolar, MOS, MESFET, whatever it is, comparison should be that. Okay. So, in a long channel device there is no problem. Who wants long channel devices these days? You want to have, when you go for VLSI, ULSI, you compress, make the devices smaller and smaller. You shrink the device size and increase the packing density. So, we should be, you can't sell a gallium arsenide MESFET better than silicon MOSFET for long channel devices. Short channel devices, we have seen now what has been happening. The short channel devices, high fields exist. For a given voltage drop across a channel, the channel length is small, fields are high. The moment fields are high, you have the velocity saturation effects. Okay? And it will come both in silicon and in gallium arsenide. It is not just proprietary of gallium arsenide that you will have velocity saturation. If you take a silicon channel length 1 micron or smaller, easily you can get velocity saturation effects. Now, if the velocity is saturated, Qn into Vs is the current density. So, if velocity is Vs is same for silicon and gallium arsenide, you won't get the benefit, because currents are same, transconductance will be same thing. That is what he said. As a result, one does not expect improved GM in gallium arsenide MESFET compared to silicon MOSFETs when the channel lengths are small. That was what is predicted, or at least believed by people who adore silicon. In fact, all of us adore silicon, but that has the lifeline of VLSI today. But if you want ultra high performance, then only you have to look into other devices. Let us see then. Experimental results, however, showed the following. Short channel gallium arsenide MESFET show higher GM. Just now we saw. When the channel length is reduced by putting N plus layer, you get GM 1.7 times that for a particular case. Gallium arsenide devices show GM values 3 to this of course you have to take it. They made gallium arsenide devices short channel, they made silicon MOSFETs, compared and said, my God, GM is higher in the case of gallium arsenide 3 to 4 times compared to that of silicon, in spite of the velocity saturation taking place. So, if you have to understand that, we have to take a look into the velocity field characteristics. So, we take a look at the electron velocity versus electric field in silicon and in gallium arsenide, and of course, I put also indium phosphide. Let us not take a look at it right now. We will take a look at this curve, indium phosphide curve, afterwards. We will take a look at the silicon velocity of electron versus electric field in kilovolts per centimeter. By the time about 30 kilovolts per centimeter reach, silicon saturates. In fact, what happens is the electrons remain very close to the conduction band itself, okay? And they do not get transferred to any other region in the conduction band. We will see, understand what I am talking of very shortly when we talk of gallium arsenide. The whole thing is because silicon is an indirect band gap semiconductor, and we will discuss that afterwards. So, as you keep on increasing the field, the velocity keeps on increasing, ultimately it is saturated, and saturation velocity is the scattering limited velocity. These are actually drift velocities. After all, there is the maximum velocity is thermal scattering, okay? The random movement which is there all the time, the electrons are moving around. There is no velocity of electrons, net velocity is 0, because hundreds of thousands of electrons are moving this way, that way, each one cancel. Net velocity is 0. But when you apply field, there is a directed movement in one particular direction, and that is the net velocity in a particular direction. Okay. That is superimposed velocity over the thermal velocity. So, the maximum that you can get is corresponding to thermal energy, thermal velocity. That is why scattering limited velocity. Now, gallium arsenide, if you take, goes like this, up, then comes down, ultimately going to the scattering limited velocity. Why should it go up like that? Now, we can see this actually gives us hope. Supposing this is what people thought initially, the velocity field characteristic, if it is here, if I am operating in the region of this portion, I have got velocities higher than this. But it will never happen, it is very difficult to focus onto this. When you go to high fields, you will be there. So, just let us see what is happening here. When you understand that, we can go back and see why you got, when you made that N plus region present, why you got better velocities, better transconductance. Let us take a look at this. Now, we have to take a look at some results which we borrow from physics. This diagram I had projected earlier, this is the conduction band bottom, this region is the bottom of the conduction band, and this diagram here, what you draw here is the energy versus momentum, energy upwards, momentum k on the x axis. How is the energy versus momentum? That if you plot in the conduction band, it is like this for gallium arsenide. Now, in the valence band, energy versus momentum is like this. I have discussed this when we discussed the direct band gap and indirect band gap material, difference between gallium arsenide and silicon. So, now, as a result of this, what happens? This region is the bottom of the conduction band. I just want to make it clear by drawing the diagram. What we are talking of is EC versus EV if we plot. We are drawing those diagrams there, one is corresponding to this region. This is the distance, but if you plot with energy versus momentum, this is the one valley, one distribution, energy versus momentum. Okay? That is E versus K if I plot. And then there is one more which goes like this, which is flatter. And here directly below that you have got the valence band. So, if you have energy versus momentum diagram like this, the implication is the electrons will move, will stay here, that is the bottom of the conduction band. So, electrons will always be occupying this position, holes will be occupying this position. Now, if you give energy to these electrons by applying field, they acquire energy, they move up. Okay? They move up, in fact, this is a continuous path. Usually that is not shown, people are happy to see this edge and that edge. This is called the upper valley. It is called valley because it looks like a valley, no other reason. And this is the central valley or the lower valley. Okay? This is the lower valley, upper valley, lower valley. Now, the difference between these two valleys is, this is sharper and the sharpness actually is reflected in the effective mass, that you have just borrow and believe on that. Okay? And this is flatter, or if you do not want to think that, that is why I have drawn this flatter. More precisely, the effective mass of electrons here is smaller compared to that. So, if the electron is in this region, effective mass is smaller. By some mean chance, if the electron is here, the effective mass is higher. Okay? If the electron is transferred from here to here, it is suddenly it finds itself heavy. If it were here itself, if it had gone up here, then half m square, m is the effective mass. If the mass is smaller, velocity will be higher. If it is transferred onto this valley, mass is higher, velocity will be lower. Velocity lower here because mass is higher, half m square. So long as it is here in this valley, its velocity is higher. So, what happens is, as you subject the electron into the electric field, its velocity keeps on increasing because it gains energy, its velocity keeps on increasing. And once it gains energy enough up to this point, okay, it crosses onto this valley, because it does not go up here, because electron always has got the tendency to occupy the lowest energy level permissible. So, it is not moving up there, from here it gets scattered onto that, because that is lower energy, it cannot go up there, it goes on to that. In other words, it gains enough momentum, this is a momentum difference, it gains enough momentum, it finds itself in that portion. So, as we keep on increasing the energy, by increasing electric field, velocity keeps on increasing. I have talked about one electron getting transferred there, that electron will find itself having a lower velocity. All the 100,000 electrons will not get transferred onto that simultaneously. Okay, this is a sort of probability. So, many of them will get transferred as keep on increasing energy. Okay. Finally, if all these electrons have got transferred onto that, the effective velocity of those will be smaller. And the mobility here is almost closer to that of silicon, because the effective mass is closer to that of silicon. And once it is transferred here, if you increase further the electric field, it behaves like in the silicon, the saturation velocity occurs here. So, the entire philosophy here, or the point that we are trying to point out, is the transfer from here to here has been possible because this energy is 0.36 electron volts in gallium arsenide. If that energy is that much high, there is no chance for the electrons to be transferred onto that. Okay? You would have got one velocity corresponding to this region, because it is 0.136, and this actually is how much? 1.43 electron volts. See, once we understand this, we can zip through the derivation of the whole thing very easily. Okay? That is 1.43. If this were 1.43, what would happen? If this were 1.43, that gap between this upper valley and lower valley, okay, if that were 1.43 electron volts, you would have got breakdown. Breakdown means what? Actually, ultimately you have the whole electron pair generated. You would have interaction between these two, because this is much smaller than that. You have got these electrons transferred onto that. Velocity drops. That is the phenomenon. In silicon, what is the difference? So, okay. So, as you increase the field, electron velocity goes on increasing because of it absorbs energy, but as it absorbs energy, when beyond a certain energy, the electrons get transferred onto this upper valley. In fact, what we can say physically is the mode of its transport slightly changes, the way it moves slightly different. Physically, you can just visualize it this way. I do not see it written in black and white anywhere, but my own thinking in that is, in between silicon and gallium arsenide, what is the difference? In silicon, the electron goes through the potentials due to the atoms. There is potential variation because of the atoms. As it goes to the nucleus, between the nuclei, it goes to the potential peaks and down. That is the only thing that is seen there by electron which is moving. That is the effective mass due to the potential changes. If there is no potential change, if there is no field within the atoms, the mass would have been the mass of the free electron. The effective mass comes up because of that potential change due to the charge in the nucleus. In gallium arsenide, there is additional field comes up. What is the additional field due to? Between the gallium and arsenic, there is net charge difference. So, there are between the two atoms, there are additional forces coming up. So, because of that, you have the effective mass smaller. That is physical concept. In terms of energy band diagram, this is sharper there. See, the effective mass itself comes up because of additional forces which are present between the atoms in the silicon, in the crystal. Here you have got extra forces which are coming up because the charge difference between the gallium and arsenic atoms. Okay. That is why effective mass is much smaller here compared to that of silicon. That is physical understanding. Now, you give enough energy, that extra force that is experienced by the electric field due to the plus and minus charge between the gallium and arsenic, it is a very small force, that is not any more effective. So, it looks as if it is like similar to that of silicon. Okay. This is a very oversimplified thinking, okay, which sounds quite good from the physical consideration point of view. So, in terms of energy band diagram, it is in fact, if you want, you can throw further jargons. Electrons get scattered from this valley to that valley. Why do you say scattered? Its mobility falls. So, whenever mobility is change is there, you say it has scattered. So, inter-valley scattering is called. It is the jargons which are put up. All that happens is the mode of transport is slightly different because the energy acquired is so much that the extra field that comes up because of the plus charge on gallium and minus charge on arsenic, that field is not no more effective, because it is so much high here. Okay. If there is a plus charge, the electron tends to move in that direction like this, but if the velocity is high, it will just not see that effect of that. That is what is a simple minded thinking on that. Okay. So, now let us take a look at this particular analysis. Quickly run through this analysis. Now, this is all I just summed up and put synchrotron radiation, Schottky barrier, electron reflectance, all those measurements have shown that delta E, that is the gap between the upper valley and the lower valley, is 0.36 electron volts. It is called central valley or lower valley. That is a quantity which they have estimated upper valley, lower valley, or you can call central valley, because it is not one valley that is present here. Central valley is there. If you go to 3 dimensional, there will be 4 valleys like that, 4 valleys like that all round. Okay. So, electrons can go transfer to that or transfer to that like that. It is a 3 dimensional in the Brillouin zone if you take. So, M1 star is effective mass of electrons in the lower valley, M2 star is effective mass of electrons in the upper valley. That is upper valley, M2 star, M1 star lower valley, central valley. Okay. I put the diagram again, so that if you miss something you can see here. 1.43 is the band gap, 0.36 is the delta E, M1 is the effective mass here, M2 is the effective mass in the upper valley. Correspondingly, mobility is here mu 1, mobility here is mu 2. This is about 8500, this is close to that of silicon here, 1500 of that order. Okay. Now, total carrier concentration, now electrons can remain here or here. So, between these two locations that you provide for the electron, if you do not give extra energy by applied electric field, they will occupy here, they will be occupying lower valley or central valley. So, N is the total number of electrons and it is equal to doping concentration, and all of them will be here at 0 electric field. Okay. As you keep increase in electric field, some of them may get transferred to that if you call it as N2, N1 plus N2, N1 here, N2 here, some of them will be equal to total. Hereafter, if you understood the phenomena, we can just go through 3-4 slides very quickly. Okay. Now, M1 star is 0.067, M2 star is 0.55, which is close to that of silicon. That is why I said, when you transferred here, the implication is the extra field that you get because of the net charge on gallium and arsenic, that effect is not affecting the transport of carriers. That is the meaning of that. Okay. N1 and N2 are the densities of electrons in the lower and upper valleys. Let us go further now. Now, hereafter what you do is write down the, how do you find the velocity related to current. So, if there are N1 electrons in the lower valley and mobility is mu 1 and E is electric field, total current due to the electrons is actually J, current density, Q into mobility into carrier concentration in the lower valley into the electric field, plus mobility in upper valley into number of electrons in the upper valley into electric field. As far as outside world is concerned, you do not care whether the electron is here or there. Okay. What you see net is the current, and you net is what you see is electron concentration N, and N is N1 plus N2. Okay. So, we can still write as far as outside world is concerned, what you measure is the velocity. So, when you measured, when you got velocity versus field, it is that what you are seeing here. So, the total current can be put as current density Q into total electron concentration into the total velocity, effective velocity, combined velocity. You can put this is the velocity, all of them are moving with the same velocity, that is velocity. Now, what we do is, therefore, velocity is equal to J, which is this quantity, J is that quantity, divided by q n. So, q get cancelled, I get velocity is equal to mu 1 n 1 plus mu 2 n 2 into E, n is outside, divided by n. Electric field is there. So, you take this n 1 plus n 2. Now, what we do is make a little bit of simplification to get through this analytically. You may have to go through numerically, otherwise you can see here. I am just neglecting this quantity compared to that. We can do that. You can neglect this quantity because of two reasons. One, mu 2 is small compared to mu 1. Mu 1 n 1 and mu 2 n 2 if you take, you are neglecting mu 2 n 2 compared to mu 1 n 1. Okay. Reason is mu 2 is smaller than mu 1, n 2 will be smaller than n 1, at least till certain field is there, because all the electrons do not get transferred immediately. Up to certain electric field, n 1 will be large. At least when all the electrons are here, that is nothing there initially. Till the electrons get an energy corresponding to that, n 2 is actually 0. So, most of the portion we can take that second term is small. What I am doing here is this derivation is available in the old book of SMJ's book on device physics. Okay. So, I have literally followed that. So, the derivation is available there. I am just going through that. Physics of semiconductor devices by Zay. So, that I neglect, I divide by n 1, you get this. Now, velocity versus electric field I can find out if I find out n 2 by n 1 ratio, that is electron concentration in the upper valley divided by electron concentration in the lower valley. Electron concentration is related to density of states at that edge. For example, we write the electron concentration at this conduction band edge here, n 1 is equal to n c e to the power of E c minus E f by k t. Okay. I call this as E c 1, I call this as E c 2. E c 2 minus E c 1 is actually equal to delta E. The difference between the two conduction, I can talk this also the conduction band edge for this. So, n 1 is n c 1 e to the power of E c 1 minus E f. n 2 electron concentration here depends upon n c 2 e to the power of E c 2 minus E f. Apparently, it is smaller because E c 2 minus E f is larger than compared to that. So, almost all the electrons will be here, but notice one thing. Okay. Now, let us go back to this further. n 2 by n 1, I am just putting the T e there. In all the cases, I put T e there. Okay. Because if T is equal to T, T is equal to T, where T is the lattice temperature, okay, you will find that n 2 equal to 0. Let me go through the thing and see. So, let the T remain as T e now. Okay. We will examine it again. So, n 1 by n 2 is actually given by n c 2 by n c 1, n 2 by n 1, n c 2 by n c 1 into e to the power of E c minus E c 2 minus E c 1 by k t, which is actually equal to density of states here divided by density of states here multiplied by e to the power of minus delta E by k t. Okay. Now, I have replaced T by T e. T e is actually the electron temperature and T is the lattice temperature. Usually, we use T is equal to T, temperature is lattice temperature. We do not talk of hot electrons. When I say T e, the temperature of electron is higher than that of lattice temperature, means it is not in thermal equilibrium with the lattice. It has acquired so much energy that it has gone to into a different total mode of operation, it has gone into the upper valley. So, that is actually you are talking of hot electron. Like when the Schottky barrier we talked of electron being injected into the metal having higher energy than that of the metal, that is hot electron. Here also you are talking of a device in which the electrons are hot. When you say electrons are hot, I repeat whatever I said earlier. The implication is the electrons have energy in excess of kT corresponding to kT, temperature T, where T is the lattice temperature. If it is T, lattice temperature, it would have remained here. It would have been just around that distributed up to certain height, but they are taken up into higher value. See, the implication is, supposing I draw a conduction band, okay, you get the electron distribution like that from EC here. What is the meaning of that? This is thermal equilibrium situation. Supposing they raise the temperature of the electrons, what happens? These electrons move up. The electron, if it is here, that does not correspond to the situation where the electrons are in thermal equilibrium with the lattice. So, this electron will be hot electron, which does not obey this law corresponding room temperature, but still you can write those equations taking a temperature which is corresponding to that. If I distribute the whole thing up there, you will get a distribution which goes up like this. You will get a distribution which goes something like that beyond thermal equilibrium. Those, that is, then you have to change T to TE. That is what you are doing. You change the temperature of, you write the equations corresponding to the temperature of the electron, that is higher energy. Okay. So, the most important thing now is N2 by N1 is Nc2 by Nc1 into e to the minus delta E by kT. Out of these, we know delta E, 0.36 electron volts. Nc2 by N1, Nc is that quantity. So, T you write T of course, and Nc1, Nc2 by N1 will be equal to, taking the same temperature for the electrons, Nc2 will be Mn star 2, M2 star, Nc1 will be, this will have M1 star. So, M2 star by M1 star to the power 3 by 2. What is another N2 by N1 coming up there? Number of, okay, total density of states in the upper valley, total density of states at the lower valley, it would have been M2 star by M1 star to the power 3 by 2 ratio, if there is one valley here, one valley here. Now, what is happening is, if you go to 3-dimensional picture, central valley is 1, there are 4 such valleys. So, that N2 that I put the N2 by N1 that is on the right hand side there, okay, that quantity, this is number of valleys. Upper valleys there are 4, lower valleys there is 1. So, N2 is 4, N1 is 1, that is number of upper valley is 4, number of lower valleys is 1. This is slightly getting into a little bit of physics, but we borrow those results and believe in those physicists and say that is all right. Okay. Comes from the Brillouin zone analysis. Now, M2 star is 0.55 into M0, M1 star is 0.067 by M0, and N2 by N1 is 4. You plug in all that, this is 94 for gallium arsenide. For different materials, that will be different. So, that is 94. So, now we see what we, if you recall, what we did was, I will retain that equation. Velocity is mu 1 into electric field divided by 1 plus N2 by N1. Okay? That is what we did. And N2 by N1 is Nc2 by N1 into e to the power minus delta E by kT. Nc2 by N1 just now we saw it is 94. So, that is the thing. And remember that T is not T, it is T all through. All these equations are valid for the hot electrons because they have energies above the lattice temperature. Okay. Now, I can find the velocity versus electric field from this equation. This is the equation that I must use. Okay. So, T is the unknown quantity. You find out T e by using this equation. What is this equation? See, this quantity 3 by 2 k T e minus T is actually the energy of the electron over and above the thermal energy. That is the energy acquired by the from the electric field. Okay. What is this quantity? This is the velocity. Oh. Okay. What is that quantity? Tau e. Tau e is the energy relaxation time. Meaning of that, relaxation time. You apply an electric field, the entire distribution of electrons versus in the energy has got affected, they have got excited to higher energy state. Now, you remove the electric field, they will drop back to this original state, thermal equilibrium state. The average time required for the electrons to get back to the thermal equilibrium state, that is the relaxation time. You excite a fellow, give the time for the fellow to relax. Okay, it depends upon the particular particle. So, here electron will have a relaxation time of the order of picoseconds. Okay. So, what we are telling is you excite it, and by the time it has relaxed back, that is the energy that is lost actually. So, this quantity that you have put here is the energy that is lost when it relaxes, and right hand side. So, what we wrote there you can see Q into V is the energy, Q into electron volts. So, this is actually charge into voltage by distance. This is energy, charge into voltage by distance, this is distance by time, and this is time. So, I get cancelled that, the whole thing is dimensions of energy. I am just showing you that when you write like this, this is the energy that has been lost in that relaxation time tau e. That is, in that time, whatever energy was there, it has lost and come into thermal equilibrium. So, this quantity you put it as 3 by 2 k T by T. This is the energy of the electron. The relaxation time, it will lose that much of energy. So, you make use of this concept, okay, and rewrite that. I am almost to the end of the derivation. I just rewrite that same equation, this equation, I get it as T e in terms of T. Whatever equation we have written here, previous equation rewritten here. So, what we are trying to find out is T e, because once we know T e, you know N2 by N1 ratio, because 94 into e to the power minus delta e by k T. So, here velocity itself is a function of T e. So, plug in for velocity, you get T e is equal to T plus 2/3 of Q tau e electric field by k, and V is equal to mu 1 into E, that is become V squared, divided by 1 plus N2 by N1. N2 by N1 is nothing but 94 e to the power minus delta I by kt. So, all that we have done is we have used that electron temperature, and that unknown quantity can be found out from this equation. Tau e is a relaxation time known, E is what electric field that you are talking of. What you are trying to find out now is, with the electric field, how hot the electron becomes. There are two on both sides, you have got T. It is a transcendental equation. So, you have to solve it numerically finally. So, once you solve this, you get the temperature, and once you get the temperature, you substitute in N2 by N1, substitute in velocity. Velocity mu 1 E1 divided by 1 plus 94 into e to the power minus delta E by k T E. T got from this particular transcendental equation. Once you do that, so you plot that, you find out the temperature and substitute in that equation, you get N2 by N1. N2 by N1 is this. In fact, this is N2 by N1 plus N2. On the right hand side axis, if you see, it is 0.2, 0.4, 0.61, etc. N2 divided by total electron concentration. So, you can see corresponding to E peak of about 3 kilo electron. This is calculated things, what I am plotting. Okay. At 3 kilovolts per centimeter, that is the point at which N2 starts beginning to increase. Till 3 kV per centimeter, N2 is equal to 0. What does it mean? Till you apply electric field equal to 3 kV per centimeter, all the electrons are here. So, all the electrons keep moving with the velocity corresponding to higher mobility. So, all these electrons are moving up with that mobility. They are not subjecting to the velocity saturation or anything, they are actually keeping on increasing. That is why it shoots up, and once you reach 3 kV per centimeter, the transfer of electron to the upper valley starts, keeps on increasing. As more and more increase, Qn into V, part of them have a lower velocity, the velocity, effective velocity falls. If you look into the equation, J is equal to Qn into V, where N is N1 plus N2, okay, mu n N1 plus mu 2 plus N2. That N2 keeps increasing. Previously it was mu 1 into N1, it is N1 falls, N2 increases. So, the effective velocity falls down. Okay. So, the transition point is this 3 kV, and you can see if you have a different material whose delta E is different, if suppose delta E is higher, what will happen? What will happen to the transition voltage or field? It should increase, because you need more energy to transfer electrons from here to here. That is what is happening in materials like indium phosphide. So, this is the whole thing that you have here, that this is the steady state characteristics. I have not yet come to the transient conditions. We will discuss that in our next lecture, but right now we will take a look at the indium phosphide. Indium phosphide also is a 3-5 semiconductor. I am putting this down because it is competing with gallium arsenide for high speed devices. Okay. Reason you will see when you see the plot of velocity field characteristics. So, now here you can see that is 1.35, that is 0.53. In the case of gallium arsenide, this is 1.43, and delta E is actually 0.36. So, what you will say is immediately is, if you have transfer of electrons from here to here, you would need much more energy, much more electric field. Okay. Now, that means by the time it is transferred from here to here, it would have acquired much more energy, okay, much more velocity. Now, the effective mass here is not as much as high as that of gallium arsenide, as low, but slightly higher, 0.077. That gives the mobility of electrons in the indium phosphide slightly lower than that of gallium arsenide, about 4,500 or so. So, this is smaller, or around 5,000. Okay. So, here this is almost comparable. Now, let us see what happens because of that. Because of that, gallium arsenide, you can see it gets accelerated fast. See, the slope is higher here. Notice these 3 curves: silicon, gallium arsenide, indium phosphide. Mobility of electrons is much higher than that of silicon. So, E is equal to mu into E, steeper compared to silicon. Mobility of electrons in indium phosphide is smaller than that of gallium arsenide. So, slope is slightly smaller. Okay. V is mu into E here. Now, the transfer of electrons takes place here at 3 kV per centimeter, whereas the delta E in the case of indium phosphide is almost not double, at least this is 0.36, that is 0.53. So, the transfer of electrons to the upper valley takes place, that is transfer of electrons from here to here takes place at a much higher energy, that is at a much higher field. 10.5 kV per centimeter, and by the time it has acquired energy, the velocity has gone up beyond that, and it takes much longer to transfer all the electrons to the upper valley. See, to get into this position, almost all the electrons will go into that position. So, that is why what you get now is a velocity field characteristics which looks like this. From the low field mobility point of view, that is gallium arsenide is the best among the 3 devices. From the velocity saturation, if you only take a look at, there is no choice. All of them seem to be behaving almost same. In fact, I have seen some people degrading gallium arsenide, putting this slightly below this quantity. I do not believe that. It is almost same, because after all the mechanism of transfer is the same. Indium phosphide has velocities higher than that of silicon over a wide range of field. Gallium arsenide has got higher velocities higher than that of silicon over a certain field range. So, these things make quite a bit of difference in performance. So, we will see the transient situation. What we have seen now is if you keep increase the electric field, keep it at certain value, okay, 3 kV per centimeter, that is the steady state velocity. But now, if I launch an electron from cold to that high field suddenly, what will it feel? It is not here, it is here. From there to there it has to move. There is the transient conditions. In the transient conditions, you will see what is known as a velocity overshoot effect. That is the whole cause for success for gallium arsenide and indium phosphide. We will see it in next lecture. Very interesting, do not miss. Okay.